All right, so last class we looked at this frustum of the paraboloid formed by revolving the shaded area around the z-axis. So by inspection we could tell that the centroid was going to lie on the z-axis because it's symmetric about the z-axis. So x bar and y bar are going to be 0. Z bar we're going to have to find by this integral. We're not ready to do the integral yet though. We did decide that the volumes, the differential volumes that we would have would be these disks. So the disks would be of thickness dz, and they'd have an area that we would have to calculate. So now we're going to look over here at the equation, and which of these variables is going to represent the radius of this circle? Y. Yes. A is going to be the maximum radius. So at z equals 0, A is going to equal y, but the radius is going to be y. It's x and y, but x isn't in the equation. So if the radius equals y, then that area is going to be equal to pi y squared. That's that area. All right, but it looks like we're going to be integrating with respect to z, so I need to express y in terms of z. All right, so how would we solve this for y? Oh, I can see College of the Rockies now. Right, so we're going to get rid of this factor in the front first. So we would have z a squared over h equals a squared minus y squared. Okay, actually I'm gonna go a squared 1 minus z over h equals y squared. Right, a root 1 minus h equals y. Okay. So that is going to be used in there. Because now my area is going to be pi y squared. So pi, this is y squared right here. A squared 1 minus z over h. That's the area. And then times dz. So we can figure out the total volume by integrating that. But before we integrate, let's take out this constant in the front. Okay, and what are our limits of integration? All right, since we're only looking for the frustum, That's h over 2. I'm going to go from 0, h over 2. Okay. Compared to the integrals we were looking at for the line segment last week, this is an easy integral. So when I integrate dz, I end up with z. When I integrate z over h, we end up with z squared over 2h. I'm going to evaluate that between 0 and h over 2. At 0, both of these terms are 0, so we really only have to put in the values of h over 2. So I put h over 2 in for z here. And if I put h over 2 for z here, this is going to be h squared over 4 divided by 2h, which would be, nope, h over 8. We had h squared over 4, and then we divided by 2h. That's h over 8. So basically we have 1/2 minus 1/8, which would be 3/8. So that would be 3 pi a squared h over 8. That's my volume. To find my z bar, I've got the denominator. I need to now find the numerator. What's my z tilde going to be for this volume? What's the centroid of this disk of thickness dz? Now, the disk has differential thickness, so basically all of its volume is concentrated at the same level of z. So this z tilde is just going to be z. The whole volume is at the same value. So our z bar equals the integral of z dv over integral dv. So that's going to be the integral of z times our dv, which was pi a squared 1 minus z over h dz over this integral, which we already know is 3 pi a squared h over 8. All right. So we can take constants out here again. That's going to be pi a squared integral. Bring the z in there, so that's going to be z minus z squared over h dz all over 3 pi a squared h over 8. So let's get rid of the pi's, get rid of the a squareds. and we're integrating between 0 and h over 2 again. So that integral becomes, what does the z become? Z squared over 2, and the z squared over h becomes and that's evaluated between 0 and h over 2. And we still have to divide by 3h over 8. All right, so if I put h over 2 in for this, it's going to be h squared over 4 over 2, which would be h squared over 8. And if I put h over 2 here, that's going to be h cubed over 8 divided by 3h, which is going to be h squared over 24. All over 3h over 8. So it's 1/8 minus 1/24. So it'd be 1/12. So, or h squared over 12. So that's going to be h squared over 12. And I'm going to flip this one times 8 over 3h. Yep. 8h over 36. Can you simplify that? Two h over 9. 2h over 9. So 2h over 9 is just under a quarter h, or under half the height of the frustum. So does that make sense? But that seems reasonable, so we would go with that. That's also the value that I got last year doing it slightly differently, so I think we can go with that one fairly safely. And it was much easier integration. All right. Most of the time, fortunately, we're not going to have to do these difficult integrations, or even easy integrations, because most of the time the objects that we're dealing with are regular shapes, or even semi-irregular shapes, but that have tabulated values for their centroids. And they're made up of a number of different shapes. So a composite body consists of a series of connected, simpler shaped bodies such that the composite body can be sectioned into its composite parts for weight and centroid calculations. So the formulas are very similar to the ones we looked at for the continuous objects, except instead of being integrals, they're sums. So each of these x tildes is the centroid, the x centroid, the y centroid, the z centroid of the piece of the composite body. And each of these weights are the composite pieces. So if I add up all of the composite weights, then I end up with the total weight, which is what we're going to be dividing by here. If I add up all of these are basically moments that we're adding up. We end up with the total moment. Through the division, we end up with the centroid. So these are done for weights. If we do the centroid of mass, or centroid of volume, or centroid of area, or centroid of length, they're all going to be similar. Note also that areas, volumes, and centroids of some common geometric shapes are given on the back cover of the text. So if we'd had even a paraboloid area or an x-parabolic area, we could have looked up the centroid in the back. The cubic that we did isn't in the back, so we had to do that one by integration. But a lot of them, you just use tables. So procedure for analysis: using a sketch, divide the body into a finite number of simpler shapes. Usually the lowest number of shapes you can draw it in is going to be the best, right? If you can draw something as 5 different shapes, but you can also draw it as 3 different shapes, it's going to be fewer calculations to do the 3 than the 5, and probably less likely to make a mistake. If the composite body has a hole, then consider the hole as having negative weight, mass, and volume, and area. Establish the coordinate axes on the sketch and determine the centroid or center of gravity for each part. Apply the centroid or center of gravity equations for the composite body. And if the object is symmetric about any axis, the centroid will lie on the axis of symmetry. So we can use that, as we did in the last problem, to basically make it from 3 different coordinates to 1 or 2. So here's our first sample problem. We want to locate the centroid of the cross-sectional area of the channel. Just before we go, I want to do something here. I'm going to clone this page. So this might be a piece of steel, structural steel or something, and we want to find its centroid. Because if it's a beam, then the next step would be to find its moment of inertia about the centroid, so we can calculate how much it's going to deflect in the middle and what the stresses are on the ends. We're not going to quite get to that in this course, but we'll have all the basis that we need to do it. So what's the first thing we should do? Okay, well they've already given us a frame of reference, so that's good. So we could divide it into smaller chunks. How many sections would you like to make it into? 2 of them are identical, except that they're not in identical places, locations. So you would like to have 1 rectangle on this side, and then the 2 rectangles top and bottom. Okay, where should I draw the boundary? Because there's 2 ways I could draw the boundary, right? I could draw it as a vertical line here, or I could draw it as a horizontal line. It doesn't really matter. The only reason for possibly going, oh no, that's not true either. Okay, so we'll do a vertical line. So we'll section them. Here and here. So we're going to call this area 1, this area 2, and this area 3. No, because it's in a different location. To calculate the total area, yes. But to calculate the centroid, no, because we're going to have to multiply by a different y value for those 2. Okay, before we go any farther, are there any axes of symmetry that we can use? Is it symmetrical about any vertical axis? No, because I've got the plate on this side and then nothing on this side. Is it symmetric about any horizontal axis? Yes. So where would I draw the axis of symmetry? At half the height. That's right. So we would draw an axis of symmetry like that. So what does the axis of symmetry tell us? The axis of symmetry is at half the height, which should be at 12 inches.
Is that where the centroid is?
That is where the y-centroid is, yeah. So a horizontal axis of symmetry goes through the y-centroid. If there was a vertical axis of symmetry, that would go through the x-centroid. So y bar equals 12 inches. So that means we've cut our work in half. Now we only have to find the x bar. Okay, so how are we going to find the x bar? Let me just copy the formula over. This is the formula that we're using, except instead of weights, we're going to be using areas. Okay, so that's going to be x tilde area. So for these calculations, we need to basically find for each of the three areas the x tilde and the area, and then we're going to sum them up. We can do it just on the sheet. Usually something like this, especially if there's like more than 3 parts, I would like to use a table because it helps to kind of organize all of the information, and then it also helps us when we're going to add them up because they're going to be in columns. So we would create a table then that has area or section number. Let's just call that section. Section, area, x tilde, and x tilde times the area. So section 1, which is the top, its area is going to be 1 inch times 9 inches. That'd give us 9 inches squares. 9 inches squared. Where would its x tilde be, its centroid? Well, its centroid is going to be in the center of it.
So then 4.5 degrees plus 1.
Right. It's 4.5 inches from the edge of that section, but that section doesn't start until x equals 1. So it'd be at x equals 5.5 inches. And then we would multiply that x tilde times a. 49.5. That'd be 49.5 inches cubed. Okay, what about section 2? Section 2 has an area of 1 inch wide by 24 inches tall. So 24 inches squared. Where's its x tilde? Where's its centroid?
5 inches.
That's right, it's at half of the thickness, or 0.5 inches. So that should be 12 inches cubed. area 3 is the same as area 1. So it's going to be 9 inches squared, 5.5 inches to the centroid, and 49.5 inches cubed when we multiply them together. So the last row in our table is the composite. So the composite we get from adding up this column. So 9 and 9 is 18, and 24 is 42. 42 inches squared. And then 49 and a half and 49 and a half would be 99 plus 12. Would be 111 inches cubed. And then this time we're not adding them up. We're going to take this and divide by this. So it's going to be 111 over 42 equals 2.64 inches. And that's our answer. Does that seem to make sense? This is a total of 10 inches wide. 2.64 is going to be about a quarter of the width, so somewhere around there. That seems about right because we've got a lot of material over here on this side and we don't have any material on this side. Okay, can anybody think of a different way we could have solved that? There's one way that we could have solved it that would have been faster. We did it with 3 sections. Can we do it with fewer than 3 sections? Okay, the top half and the bottom half would still be, each one of those would have to be kind of section. I can do it with 2 rectangular sections. How can we make that shape out of 2 rectangles? Anybody?
You made out a big rectangle on the outer shape with an inner rectangle?
That's right. We have an outer shaped rectangle, 24 by 10, and then we have a hole that we cut out of it, a rectangular hole. So then we've only got 2 rectangles to worry about. So that's why I cloned the page. We're going to solve it using that method. So alternately, we can consider a rectangular beam with a rectangular cutout. So this time I'm not going to call them 1 and 2, I'll call them A and B. So A equals the 24 by 10 inch rectangular beam. B equals the 22 by 9 inch cutout. Okay, so we would do the same thing with our table. We'd have our section, area, x tilde, x tilde times the area. So section A was the whole beam, so 24 by 10, 240 inches squared. The centroid is going to be at exactly 5 inches. And 240 times 5 should be 1200, 1200. I seem to have that written down anywhere. Should be 1200 inches cubed. The cutout is 22 by 9. So what is the area? Okay, it's not 198. Well, it is 100. It's negative 198. Negative 198 inches squared. Because it's a cutaway, we need to put it in as a negative value. Where is its centroid? Nope. Because it's not in the center of the other rectangle, right? It's in the center of the 9 inches, which would be 4.5 plus the 1, so it's at 5.5. I thought you said 4.5. Okay, 5.5. 5.5 inches. And then when I multiply those together, I'm also going to get a negative result. 1,089 inches cubed. Add up these two columns. This one's 42. And this one's 111. So x bar equals 111 over 42 equals 2.64 inches. So we get the same result. A little bit easier. Not a huge amount different, but a little bit. All right, so this time we have a concrete retaining wall. So it's sloped back. This is holding back the earth. So it's going to have pressure on it from the weight of the earth here, and potentially it's going to have a hydrostatic pressure on it as well if the soil is saturated. And we see this shape here. This is actually fairly important, that this part here is projecting out to the right. So that's going to help to keep it from tipping. So it actually has weight on top of it now that's going to help to prevent the retaining wall from tipping. So locate the center of mass of the concrete retaining wall. They've given us the axes. Are there any axes of symmetry that we can put on here? Well, it's not symmetric horizontally, right, because it's skewed to the right. And it's not symmetric vertically because it's a lot fatter at the bottom than it is at the top. So this time we're going to have to calculate both x bar and y bar. How many sections am I going to have to divide this into? What are the 3 sections you're suggesting?
The bottom rectangle and then putting that coverage in.
Okay, so definitely agree on that one. We'll cut off the bottom rectangle. So that's going to be, that'll be section 1. Now for finding the centroids, I mean, yes, I could make this into 2 triangles, but if I draw this line here obliquely, then the location of the centroid in relation to the x and y axes is not going to be easy to find. So I'd be better to cut the top bit into 3. So 2 right triangles that have sides parallel to the x and the y axis, and then a rectangle in the middle. So we'll call that one, since it's a rectangle as well, we'll call that one 2, and then we can go 3 and 4. Okay, so we need to do a little bit of geometry. 1 is pretty easy to see what its dimensions are. What's going to be a little bit more challenging is figuring out these widths here. Right, so that one's going to be 0.6 because it's the same, this is flush here. So this one starts at this point, that's going to be 0.6. And because it adds up to a total of 1.2, this one's also 0.6, even though it doesn't look like they're the same, they are the same. And what about this width here? Well, it's 2.4 plus 0.6 is 3 to the side, and then back 1.2. So that would be 1.8. All right. So now we can create our table. Our table this time is going to have 2 extra columns because we have to find the x centroid and the y centroid. So we're going to have an x tilde and a y tilde, x tilde times a, and y tilde times a. All right, section 1. Section 1 has an area that's 0.4 times 3.6, I get for the total 1.44 meters squared. Okay, and if my origin is here, where's my x tilde?
1.5.
Right, so this was a total, so let's write that total distance in here. Total distance here is 3.6 meters. So x tilde is half of that distance, 1.8 meters. What about y tilde? 0.2. Right, which is half the height. Okay, so then we're going to fill in the table by multiplying x tilde times the area. 2.592 meters cubed, and y tilde times the area. And that's meters cubed as well. Okay, section 2 is the rectangle here in the middle. So it has a height of 3 meters and a width of 0.6. So that'd be 1.8 meters squared. Its x tilde is going to be at the start of the rectangle is going to be at 2.4, 1.8 plus 0.6, and then it's going to be halfway across it, so another 0.3. So 2.7. And its y tilde is going to be half of the 3 meters, so 1.5, plus the height that it starts at, which is 0.4. 1.9. Okay, and then we can multiply those. Somebody check these. I don't have the numbers written down. So 4.86.
Yeah.
If anybody's getting a different answer, please let us know before we get too far. 3.42.
Dennis,
Yep.
when do you get to 2.7 again? I missed that.
Okay, so the 2.7, it's 0.6 plus 1.8 is 2.4 to the left edge. So it's 2.4 to the left edge. Then halfway across, excuse me, is another 0.3, so half of the 0.6. So 2.4 plus 0.3 is 2.7. It's also, you can look at it as 2.4 to this side and 3.0 to this side. So the average is going to be 2.7.
Okay, thank you.
All right, now we're up, excuse me, now we're up to the triangles. So triangle 3 has a base of 1.8 and a height of 3. So if the area is 1/2 base times height, or 0.9 times 3 should be 2.7. .7 meters squared. Where is the centroid of the triangle? Right, or it's 1/3 of this, of the 1.8 from the side here. So it would be 0.6 this way. So that'd be 1.2 plus the 0.6 is going to be 1.8 from the y-axis. And what about the y tilde? That's going to be 1/3 of 3 up from the flat side. plus the 0.4, 1.4. Not 4.4, 1.4. And we can multiply those. Weird. 4.86 meters cubed.
3.7.
Okay, one more triangle to go. So the skinny triangle, again, its area is 1/2 base times height. The base would be 0.6. The height is 3. So 1/2 base times height should be 0.9. The x tilde is going to be 1/3 of the distance across from the flat side of the rectangle. So 0.2 meters from here. So that would be, nope, plus 0.6. 3.2, yeah. So 3.2 meters. And the y tilde is going to be 1/3 of the way down, which is going to be 1 meter from the top, which would be 2.4 from the bottom. Okay, if we multiply those out, .88 meters cubed. 2.16 meters cubed. And for my composite, we're going to add up this column and these two columns. Anybody else get 6.84? Yep, okay. $15.192. Okay, anybody else confirm that? Yep, okay, good. 9.588 meters cubed. Anybody else confirm that? Oh, we got two different numbers for that one, so don't write it down yet. 9.648. All right. So based on those values, then we would calculate our x bar and our y bar. So x bar is going to be 15.192 over 6.84, 2.22 meters. Y bar is 9.684 or 648 divided by 6.84. 1.41 meters. Okay, let's see how that looks on the diagram. So 2.22 meters. This would be 2.4, so it'd be back a little bit from 2.4, kind of about there. And 1.41. The total height here is 3.4, so it'd be less than half of that, be a little bit lower. So we're looking probably about there. that seem reasonable? Yeah. All right. So there's one more problem to finish this section, and this one is a three-dimensional problem. So we want to find the center of gravity of the homogeneous block assembly having a hemispherical hole. So first we would partition this. Where would you like to draw the different sections?
That wedge shape and the brick and the hemisphere.
Okay, so the wedge shape, which would be a triangular prism. So I'm going to call that one 1. And then the brick, as you called it, would be a rectangular prism. So we can call that 2. And then in the hemispherical hole would be our third volume. So that means for each of these three sections, we're going to have to calculate a volume. We're going to have to find the x tilde, y tilde, z tilde of the centroids. Basically do the same thing that we did for the areas in the past two problems, except that we've got 2 more columns in our table because we have 3 components of our centroid. Is there any axes of symmetry here? No. If they hadn't stuck this triangular prism on the ends, then we would have had 2 nice axes of symmetry. Actually, no, we wouldn't, because they didn't put that hole in the center either. We'd be screwed either way. So that means we need to go through each of the sections and calculate its volume, x tilde, y tilde, z tilde, multiply them out, x tilde v, y tilde v, z tilde v. All right, so we'll start with our triangular prism. How are we going to calculate the volume of our triangular prism? Right, it's going to be 1/2 base times height times depth, or 1/2 of the volume of a rectangular prism that would have the same dimensions. So 1/2 base looks like it's oh, sorry, that is 2 1/4 and 2 1/4. That's 4 1/2. The width here is 1 inch, and the height is 3 inches. So 6.75 inches cubed we can put in here. 6.75 inches cubed. Where is the centroid? On the y-axis, it's going to be in the center. That's right. So it's going to be 0.5 on the y. What about along the x-axis? Because it's triangular in the xz plane, it's going to be 1/3 of the distance from the z-axis. So that's going to be 1.5 inches. And it's going to be 1/3 of the height of the rectangular prism, which is going to be 1 inch, but the bottom of the rectangular prism starts at z equals 3. So it's going to be 3 plus 1 is 4 inches. So 10.125 inches to the fourth, 3.375 inches to the fourth. How much?
27.
Exactly? 27.0 inches to the fourth. All right. So section 2, which is our rectangular prism or our brick. Its volume is just going to be length times width times height. So the length looks to be, that's 2.5 plus 2.5 is 5 plus 1 is 6. The width we already figured out before was 4.5. Right, same as the rectangular prism. And its height is 3 inches. Yep. 81 inches cubed. Inches cubed. And its centroid is going to be fairly easy because it's got one corner right on the origin. So the x is going to be half the distance to the far side, so that's going to be one of these 2.25 inches. The y bar is going to be half of that 6 inches. And the z tilde is going to be half of the 3 inches. $182.25. 243. And this will be half of that, so 121.5. All right. The last section is our hemispherical hole. What's the volume of a hemispherical hole? Half the volume of a sphere. So the volume of a sphere is 4/3 pi r cubed. So this is going to be 2/3 because it's half. 2/3 pi, radius is 1 inch. 1 inch cubed, but it's a hole, so it's also going to be negative. sorry, 2.094. Okay. Okay. Where's its x-centroid? Right, it's that distance here that's given as 2.25 inches to the center of the circle. Where's its y-centroid? Right, so its y-centroid is going to be the distance here from the x-axis. So that's 2.5 plus 1 is 3.5 inches. Where's its z-centroid going to be? Why would it be 2.5? It would be the center of the spherical hemisphere, but that's not 2.5. It's close to 2.5. But it's not a, if it was a cylindrical hole, it would be 2.5, half the depth. But it's not. So what we would do is we would look at the table. Does anybody have their textbook handy? I don't actually have a formula written here. The table in the back of the back cover of the textbook has the formula. I'm just trying to remember what it is. Nobody has their textbook here? Okay. Pardon? Well, I was going to actually look it up on mastering, the e-text on mastering engineering, but you could look it up on Google as well. Centroid of a hemisphere. Change this to an image. It's 3/8 of r? Okay, that sounds right. So that's from the flat side, exactly. 3/8 of r from the flat side. So r was 1, which makes it easy. So let me make a note on here. Centroid z tilde equals 3/8 of r below flat side. So the flat side is going to be 3 inches minus 3/8 times 1 inch. So that'd be 2 5/8, or 2.625. is the value I have here. Okay, now we multiply our x tilde times our volume. That's going to be negative 4.792. 712.
Negative 7.333.
330.
Yep. .490.
All right, and then we just add them up. So our total volume is going to be 85.656 inches cubed. All right, and from there we can figure out our centroid. So x bar is going to be 187.7 divided by 85.656. 2.19. Does that make sense? Okay, it's a little bit to the right of the centroid of the brick, and because the triangle on top, triangular prisms on top, that makes sense. Y bar is going to be 239.0 divided by 85.656. 2.79. So that's going to be this way of the centroid of the brick, and again that makes sense. For one thing, we've got a hole cut out of just the positive y side of the center of the brick, and then also we've got the triangular prism that's piled on the left side. So inches, and z bar 143. 1.67 inches, which again makes sense. It's just over the center of the brick because we got this weight on the top that's in addition, which is a lot bigger than the volume that's cut out here for the hole. All right. That actually finishes chapter 9, or the part of chapter 9 that we're going to do. So we have one chapter left. I think rather than do 10 minutes or less than 10 minutes, 8 minutes on it today, I think I'm just going to finish early and we'll start chapter 10 on Thursday. So chapter 10 is moments of inertia. And I just give you a little bit of the reason why moments of inertia is in this course or in this part of the textbook, even though we don't actually use it. It is used for dynamics from our physics courses, we should know that at moment of inertia, basically, it's going to give us the rotational resistance to changes in motion. So whereas something that has a lot of mass has lots of inertia, something with lots of mass located a great distance away from the axis of rotation is going to have a great resistance or a great rotational inertia or moment of inertia. That's not really why they put it in the statics course, though. They put it in the statics course because the moment of inertia of a cross-sectional area is going to be used for stress, strain, and deflection calculations for beams and columns and such. So we're going to look at moments of inertia of a bunch of common shapes like I-beams and T-beams and stuff. Just like the centroid chapter, though, we're going to look at the basis of it in terms of calculus. So we're going to do some odd shapes first, and then we're going to do some more common shapes that we can do by composites. So you would look up the moment of inertia of rectangles and triangles and hemispherical or half-circle areas, and then use the parallel axis theorem to put them all together. All right, but we won't do that till Thursday. Any questions before we break? All right, I will post the notes.